Okay, thank you very much. Welcome to my talk about bridging all Samsung cameras to Mastodon. So what is this actually about? There is a bunch of cameras that Samsung created a long while ago, actually before Mastodon was released to the public. And these cameras were equipped with Wi-Fi, and I wanted to make them work again in our modern environment and be able to send photos from the camera to the internet, to social media, or wherever you want to send them. Now, will give a brief introduction of which camera models can be used for that. Then the main part of the talk will actually be about reverse engineering, how the cameras talk to the Samsung API services. And then I will introduce my free software implementation project and talk a little bit about hotspot detection and how it can be used on small modern devices which probably have even more power than the cameras we are interfacing with. Starting in 2009, Samsung created a bunch of different camera models that were equipped with a Wi-Fi module. There were 7 different models with interchangeable lenses. There were around 2 dozens of different models of compact cameras, 2 camcorder models, and also a bunch of 360-degree cameras. So quite a different set of options. And they were produced from 2009 to 2015. And then Samsung decided to exit the camera market and stop production of everything, despite being quite at the front of what was technically possible back then. Today, the cameras are still available on the used market, so you can get them starting at 30 euros for the low-end compact models and up to 300 euros for the mid-range models, or the high-end model is, I think, something around 700 or so used. And these cameras actually implement a built-in social network service feature. So you can, right from the camera, post your pictures and videos to Facebook, Picasa, send them via email, and all that was implemented using a central API service provided by Samsung. So the cameras never talk directly to the social networks, but instead use the Samsung service. There was some kind of authentication implemented, and the Samsung service forwarded the user credentials and the pictures to the respective upstream service. I guess that this was implemented so that whenever Facebook changed their APIs, Samsung didn't have to roll out firmware updates for 20 or 30 different camera models. And depending on the model, there is a different subset of the services. So some cameras also support Vkontakte, a Russian social network. Some allow uploading to YouTube. Some only have the email feature. One way or the other, Samsung discontinued the services in 2021, disabled all the servers, and now if you try to connect with the camera, then you will just get a strange error message. Now, how does it work? Normally, the camera connects to your Wi-Fi network. It will then, through the Wi-Fi network, try to connect to the Samsung SNS API. And given that the SNS API is discontinued, it will end up in Nirvana. So what can we do about it? Well, we can capture the traffic at the hotspot access point and do a DNS redirect or HTTP redirect to our own Python implementation. Now, in theory, this is great, but what does the camera actually expect as a response? And this is where the fun begins. Given that Samsung discontinued the services before I started implementing them, it was not possible to just query the server and to see what is the expected response. So this gives us a situation where I had to reverse engineer the different APIs they're using from somewhere. So what kind of sources could we use for that? I actually had one packet capture from 2013 from one of my first experiments. Unfortunately, it didn't have the full API use in it, but only a hotspot check, so it wasn't really usable. Samsung also released quite a bunch of open source code in theory. So for some models, they had multiple gigabytes of open source downloads. None of them contains the code that we are looking for here. The cameras also have debug ports on their main board, so you can actually connect to it and use a serial port to get some sort of debug traffic. So let's look into it a little bit later. And finally, there is still a bunch of available downloads for the camera firmwares, which we can use for reverse engineering, at least if we can understand their format. And well, I have had a look into the camera app for the NX300 camera, which is running Linux and an open closed source camera binary. I've looked into another model which had the forgotten debug symbols, and looked into the firmware structure for one of the high-end models with an unknown compression mechanism. The debug port was the first avenue, and maybe you can see it in the picture. One of the pins is a little bit worn out. This is from somebody trying to get a pin to get the serial readout. And the camera actually does report things over serial when it's starting and when it's communicating with the API. Unfortunately, it doesn't tell what it doesn't like about the response from my fake server. So this was a dead end. Another camera model, the first one with Wi-Fi actually, also has a serial port for debugging. And on that serial port, it emits quite a bunch of interesting things. There is some sort of live bridge implementation. So this is some kind of network stack apparently with a Broadcom chip model number. And it turns out that this Broadcom chip is actually running on a dedicated daughter board, which is responsible for Wi-Fi, Bluetooth, and GPS reception. So quite interesting, and probably the connector for this daughter board can be rather easily intercepted to understand what kind of traffic is sent, and maybe even to get a firmware dump of this module. But so far, I didn't have the tools to follow up on that. And also nothing interesting on the serial log, unfortunately. So let's look into reverse engineering the actual camera code. Starting in 2013, the high-end models released by Samsung, like the ones here on the table, have been implementing Tizen Linux as the underlying operating system. So today you might know Tizen from Samsung smart TVs, but back in the 2010s it was used for smartphones, for TVs already back then, and also for cameras. And it was rather straightforward to get root level access to the operating system. So it was possible to install Telnet, to install SSH, FTP, whatever you wanted. The camera UI is actually running X11 with an Enlightenment window manager, so you could also intercept the screen commands, could inject keystrokes, could get screenshots. But the management of the actual camera is a huge ELF binary with no debug symbols. So unfortunately not quite easy to get into it. Given root level access, it was rather easily possible to redirect traffic from the camera just by modifying the hosts file on the camera. So from that, it was possible to rather easily obtain access to their API implementation. And the first one was transmission of emails. This is one of the example requests that the camera generates when sending an email. It is luckily unencrypted HTTP. I mean, it was designed in 2013 where mandatory encryption wasn't mandatory yet. And it is more or less a standard HTTP multi-part form data upload with an XML file that contains the email sender, recipient, message body, etc. It has a raw payload with a JPEG file or multiple files that you are going to send. And unfortunately, it is not valid multi-part form data because it is missing the terminator. So they are missing 2 dashes in the end. And the good part is that the camera just expects an HTTP OK response, and then it says, OK, fine, email sent, everything is good. And this is rather easy to implement, and server side was the first one that I got working. And this is also why the API implementation is called Samsung NX Email Server. So how does it look in practice? I'm using Python Flask, which is a very nice toolkit for rapid prototyping of HTTP endpoints. So the first line is an app route for the HTTP endpoint for posting data, and whenever something hits this URL, the send mail function gets called. It checks whether there is a message in the payload. If there is no message, then Flask is not understanding it and needs to be patched to understand the message without multipart terminator. Then it obtains the XML from the message, extracts the sender, the recipients, subject, body, and creates an email message and transmits it. So this is really, really straightforward. Now, the cameras also support social media upload. So Facebook, Picasa, etc. It's all going through a different API. And this one is still unencrypted, HTTP, luckily. It's always going to SNS gateway, samsungmobile.com, then the respective social networks that you want to connect, and authentication endpoint. And, well, this looks encrypted, kind of, sort of. We have a very, very long hexadecimal number, which is called camera crypt key. So apparently some sort of encryption. We have username and password, which are URL encoded base 64. And also binary. We have crypt session key value, which is also base 64, but not URL encoded this time. And then we have another hexadecimal number application key. Yeah, so now we have two problems. First, we need to understand what all this encryption is about. And then we need to reverse engineer the expected response, because the camera is sending this and it is expecting something in return. One point of note is that the crypt session key is looking rather suspicious with all the slashes in it. Slashes in base 64 are encoding FF bytes. So for something that is claiming to be a session key, which should be a random key probably, something is off here. Now, let's look into how this is actually implemented. The username and the password are encrypted with the session key. The session key is obtained from a function called securRandom. As a cryptographer, this is something where you are starting to get nervous, because that might be a problem if you want to understand and reverse engineer it. Camera crypt key is a session key encrypted with an RSA public key, for which, of course, the private key is not provided in the camera, but is somewhere hidden inside of Samsung's backends. Now, the securRandom function, if you look into it, so this is not the actual source code, but from a decompiled code from the NX300. It starts out with something strange. It is using the standard library, random number generator, and it is initializing it with the current time in seconds. So usually cameras have the time set more or less correct, so that the timestamp on your photos is okay. And this gives us randomness entropy of something like 10 bits, which is not really cryptographic randomness. Then we take this random number from the random number generator, which is not cryptographically secure, and format it as a string, human readable. And then we run SHA-1 hash on this. So our secure random number generator is not secure at all. But this is not the end. If we look into the SHA-1 function, it gets even stranger than that. First, it obtains the length of the number that we have just passed to it. Then we allocate a buffer on the heap that we are going to return later. Then we allocate an intermediate buffer on the stack. And then we copy the uninitialized stack buffer to our result buffer and return that. So essentially, we are just returning 20 bytes from whatever the program was running before, which is still more entropy than the second based one, but not really cryptographic wonder. And then we are putting the session key and initialization vector for the encryption into the crypt session key variable unencrypted. So we are doing all this cryptographic magic and all this, let's say, creative use of random numbers, and we are then putting the unencrypted session key and the encrypted session key into the message payload. When I first saw this, I was wondering if maybe I'm getting something wrong, because that was, well, it was too much fail for once. So I had to make a proof of concept decryptor, and this is a code. It is, the first function is for doing the standard IES CBC decryption with a key and initialization vector. And the second one is dumping the XML, getting an elementary out of it, and decoding the username and the password. And I took one of the snapshots I did with Wireshark and passed this in, and it was actually decrypting. So X and Z were the username and password I was using when calling the API, because typing on the camera touchscreen is kind of tiresome. Now, given that we could decrypt username and password, and yeah, all the other values, it was now time to get an understanding of what the camera expects in response. And the response is processed inside the camera by the web check login method, which is quite logical, and it is calling a function called getXMLString. Yeah, so apparently it's some sort of XML parser. No, it's not an XML parser. It is just looking for the string that you pass, or something like response session key, and then it is returning everything that follows this string in quotation marks. And it is writing the result into a static buffer with a fixed length, which is significantly smaller than the buffer that we are using to store the XML we received from the server. So this gives us actually code execution on most of the camera models, or at least a way to crash them. I guess somebody should follow up and do a little bit of ARM exploit chaining to get a little bit more out of this. But I was only interested in getting a correct response to the camera. So in Flask, you can use Jinja2 templates, and this is an XML file where you can store session key, persist key, and all the values that the camera expects. And I implemented that in the authentication response method. Here the first parameter is the site, so it's Facebook, Picasa, or other. And then it is getting the data from the post. It is creating an XML value, extracting the credentials with the proof of concept method. Authentication is done by just checking whether the username is known or not, because it's HTTP anyway, and there will be no additional security from adding passwords. I had to implement session management, and then render template is putting the previously shown XML file with the additional values and returning that to the camera. And it worked. Now, after the authentication, the camera is doing another post request to the Facebook, Picasa, whatever photo URL, and passing the file name of the photo to upload, album name, and a message that you can enter on the camera screen. And afterwards, it will use the upload URL gained from this post and just put that upload URL and upload the picture to it. Unfortunately, you don't know how many pictures to expect. So if the user selects one photo, then you will get one post and one put. If the user selects 5 photos, then you will get one post, one put, one post, one put, etc., etc. But you don't know in advance how many pictures to expect, which is important if you want to finalize a Mastodon post from it. And between the initial authentication and the actual picture upload, they might be months or whatever time passes until your next vacation, because the credentials or the session is stored on the camera, and when you turn it back on, if you are already authenticated, then you are authenticated. It will just send the post to the photo URL. So you need some kind of persistence of sessions on the server side. And if you want to post pictures to Mastodon, essentially the Mastodon standard API using the Python Mastodon client was straightforward to use. But there you need to make one API request per each photo to upload it as a medium. And then you need a final Mastodon post creation upload to send the text with all the media files attached, which is also rather straightforward, except you don't know how many pictures you will receive from the API, because the camera doesn't tell you. So as a workaround, I have been using the tilde character as a separator between the post content and the alternative text for pictures, because on Mastodon you are also kind of expected to provide alternative text for your photo uploads, or at least it is good practice. This gives us an easy number, or easy way to check the number of uploads, because the number of tilde characters corresponds to the number of pictures, if the user did it right. Unfortunately, the input box on the camera has a very limited length. So it's like, I don't know, 60 or 80 characters. It also varies by model, so you need to be creative with your alternative text. Here on the right, you can see an example. Camera to Mastodon is the actual post text, and photo of tree and photo of camera are the alternative text for the respective pictures. Yeah, all this got implemented as part of the Samsung NX email service project. It is available on GitHub, but I guess I'll have to migrate to some other repository given the current political situation. And it does all the standard functions. So you can send email using a smart host. It will just forward everything that you send as an email. You can post pictures to Mastodon. You can pass uploads to shell commands on the server where you're running it, or you can use iNotify for files that you store somewhere in the file system. And there is a little bit of routing logic in the implementation so that you can actually steer from the camera what is going to happen with the uploads. The whole project is 500 lines of code. It has a config file, a main implementation file in Samsung server.py, the XML decoding and decryption, session management, because the standard session code in Flask didn't provide what I needed for the persistence. And there is a helper tool to obtain Mastodon login credentials, which you can just run, and then it will emit a secret file that you can use for the client for uploading. And if you enable insecure downloads, then it will also serve the files that you have uploaded to it over an unencrypted web interface. So this is primarily meant for private deployment and not to be run on some cloud service. And therefore, authentication is based on a wide list of sender addresses. So whatever you enter here will be accepted, and if you try to connect from some other account name, then it will just not let you upload anything. Not really secure. Passwords could be implemented, but I didn't bother because it's unencrypted anyway. And you can define different actions. So you can say for a certain type of upload that it is supposed to go to Mastodon, to be stored, to be called into a shell command, or just dropped. So this is mainly for test purposes. You can upload to the camera API to test it, and then the file will be just deleted. And the actions are based on the social network service that you are using. So for example, if you select Facebook on the camera, in this example, it will create a Mastodon post using the standard profile. And if you select Picasa, it will use the Mastodon public profile. And the public profile is a kind of inherited profile that takes all the standard settings from the Mastodon profile and overrides the visibility. And you can define a post script, you can select different accounts, you can essentially configure it as you like. I have omitted the configuration for shell scripts because it will be a little bit longer. And this gives us rather great flexibility, and you can use it as well for emails. So if you give a recipient email address, you can also override it. It will be then removed from the list of recipients. So you can actually send a message to, for example, Georg@photog.social, and also to a real email address. And then it will be delivered both as email and as a Mastodon post. Well, that was a straightforward part. The really interesting part is the sort of things that the Samsung engineers didn't do right or didn't consider properly when implementing the code. So the first example is a missing multi-part terminator, which is consistent between all camera models that I have tested. Apparently they didn't read the RFC for HTTP, or I don't know, but it's actually a one-line fix to Flask, so it's not really a problem. Another issue I really had to fight with is TCP segmentation. So TCP is a byte-oriented protocol, which means that whenever the message is complete, it is complete. Unfortunately, the network stack used by Samsung expects the whole response in one TCP segment. So, and yeah, Flask by default will send the headers first and the body of the message later, which then causes the camera to just reject it, which is of course ignoring all the standards. Luckily, there is easy override as well. You just need to enable TCP cork, which will then let the TCP stack wait a few milliseconds and then combine the headers and the payload into one message and return that as one TCP segment, making the camera lucky again. Another very interesting thing was an off by 4 error with one specific camera model. It was really happening with just one of the models. And the issue here is that the camera, when it is uploading an email, is sending a content length header. It tells the server how many bytes to expect. And then the actual payload is 4 bytes longer than that. So any standard network stack and any standard web server will just cut off the remaining 4 bytes. I haven't found a workaround for that yet. It needs some patching, but the problem is that the camera doesn't tell the server that it is the specific model. So you need to find a workaround that will not fail to process uploads from complying cameras. And the off by 4 is not actually a static value, but it is off by 4 for each picture that you are uploading. So if you are uploading 3 pictures, then it will be off by 12. And you need to parse the content before you can figure that out, which is kind of weird. So I don't know how best to solve this yet. And my favorite quirk actually is the hotspot detection in the cameras. So what does hotspot detection mean? Well, you have often hotel Wi-Fi networks and other ones where you need to log in before you are allowed to send traffic to the internet. And the Samsung engineers realized one day, it wasn't the case in the first model, but in the second or third that they released, they realized that if you are on a hotspot network, then the camera can't reach the API. So they need to fall back into the browser and let the user enter credentials, pass a credit card number or whatever before they can access the internet, before they can upload their photo. And there are actually different kinds of hotspot detection that have been implemented by Samsung over the years. The first one is from the second Wi-Fi enabled camera model. The message is certification is needed from the access point. Connection cannot be made at this time. Call ISP for further details. If you have ever called your ISP, you can imagine that this is not going to work out. Luckily, the workaround is rather easy for this one. So the camera is detecting that your API service is running on a 192.168 IP address, which is one of the predefined ranges for private networks. And if you put the API implementation on a 10.something IP address, which is also a private network, the camera will not detect it as a hotspot. So consistency was not the main feature of Samsung engineering, I guess. And yeah, some of the cameras, like the bigger ones, they just worked. Didn't have to take care of hotspot detection. The SH100, you just have to change the IP address. And then there are still some other models where the hotspot detection just had issues. It was just not working quite right. For example, with the WB850F. And when you connect with this camera to the Wi-Fi network, it will tell you, do not enter personal information for a purchase with your credit card on your camera. So this is about paid hotspots, I guess. And then you tap OK, and then this happens. Security error, couldn't authenticate server. Well, the security error is probably because the camera's network stack is from 2013, and today you will have TLS 1.2 or something like that, which is just not supported properly. Or, I don't know, maybe elliptic curve certificates or whatever the camera doesn't like. But you get this instead of uploading your photo, and you can press menu or you can press exit, but you cannot get to the part where it is actually uploading. Bummer. So we need to look into the firmware of this camera after looking what happens on the network. And on the network, the camera is doing a request to yahoo.co.kr. So this is a Korean Yahoo web page. And the response from the Korean server is, at least in 2025 and was also in 2024, a redirect to yahoo.com, their international site. And yeah, some of the cameras were asking for Yahoo, others were asking for msn.com. And yeah, apparently the response, redirect to yahoo.com, didn't suffice for the camera to understand that, yes, it is on a public network. I tried to feed it the Yahoo homepage snapshot from archive.org from 2014. It didn't help. So I had to reverse engineer the firmware. Luckily, two of the camera models have in their firmware download archive an interesting file called partialimage.o.map, which is not actually flashed to the camera, but it is still there in the zip archive. And the firmware file itself has some kind of a partition record with a bootloader, some resources, and a file called main image. And surprisingly, the partial image map is a symbol map for the main image. So the main image is a firmware file, and the symbol map tells us which function is at which address in this firmware file. So this is actually a treasure trove for reverse engineer. I think there were like 70,000 different function names, but we are only looking for one that is, has to do with Yahoo, and it was def HTTP response start. It took some days to figure out what the function is doing. I'm sparing you the source code, but in fact, there are two possible responses that the function anticipates. One is an HTTP OK, and in that case, the response must contain a cookie on some Yahoo domain. And if it is a redirect, then the redirect URL must contain Yahoo dot at a position rather early in the response. And now comes the problem. The length of the location URL with HTTPS is 12 characters. So because Yahoo rolled out HTTPS sometime in, I don't know, maybe 2014, this response won't be taken by the camera as, yes, we are on the internet. Instead, the camera will say, oh, no, I can't. I must be on a hotspot. You need to enter your credentials, and will then loop into the screen that we have seen on the previous slide. Luckily, once we know this, we can also work around it by just responding for the Yahoo web page on our API implementation. So this is rather easy. We just check if the request is going to yahoo.co.kr, and if yes, then we are sending it an HTTP 200 OK response and set a cookie with arbitrary names on the Yahoo co.kr domain. And we can send photos. Yahoo! Now, there were different variants of that. Some were using Yahoo, some were using MSN, some were expecting only the cookie, others were expecting the redirect. And all of the cameras are sending the same request. So there is no model number, no version number, nothing to discern the request. So the solution was to just alternate between the redirect and the cookie response. And the camera will just poll the site in the background every 10 seconds. So you will get this weird screen, do not enter credit card information, for 10 seconds until the camera requests again. And then it will pass the detection because the second response is correct. And this actually helps with bringing the majority of their compact camera models online. So we have, oh, this is actually incorrect. This is 26 of 27 camera models. Now for the last one. So the last one is this little gem. And it is one of the smallest interchangeable lens cameras, which is a nice feat on its own. And actually, in 2015, Samsung was planning to release an NX Mini 2, which was based on Linux. And I really curse Samsung management from back then for stopping their whole camera activities. So they submitted the Linux-based NX Mini 2 to FCC, but then they never released it. So maybe one day somebody will find one in an old Samsung warehouse and put it on eBay, and maybe it will not cost a fortune, and then I will gladly add it to my collection. Anyway, the NX Mini 1, this one, sometimes just works and uploads easily, and sometimes it will fail and fall back to the hotspot detection, and sometimes it will just crash and hang in the uploading dialog forever, and you have to pull out the battery to make it work again. Unfortunately, the firmware is using some sort of compression that is unknown. So this one is a direct extract from the firmware file, and this is the license string for WPA supplicant by Joni Malinen. And WPA is dual license GPL, and I'm not sure if it's BSD or some other permissive license, so Samsung isn't doing any sort of GPL violation here. And you see that the strings are rather garbled, and this is some sort of compression that was new to me at least. And so I had to put it aside for quite a while. And also there is no decompression for this compression algorithm in the bootloader, which you would normally expect. So when you analyze firmware and it has unknown compression, then you will usually start with the bootloader and it will have a decompressor, decompress the firmware, and then run it. This was not the case, which is rather strange because somehow it needs to get decompressed before it can be run. And yeah, I put it aside until sometime in May 2025. There was a nice thread on Mastodon about cameras or other devices that are running the iTron operating systems, and I chimed in and said, hey, here I have one model. And I got a response from Igor Skoczynski, who is an engineer at Hextrace, which are making the IDA Pro disassembler, which is one of the industry standard tools for reverse engineering. And Igor pointed out some very interesting things, and together we were able to understand the firmware headers, which were showing what kind of partitioning is used inside of the firmware file. And what's even more important, he pointed out that this is actually a variant of the Lempel-Ziff Storer-Szymanski compression algorithm, of which I never heard before. So I think that there's a bunch of Lempel-Ziff algorithms that are rather known, but this one was really new to me. And together we worked out how the compression algorithm is used, how it works. We figured it out just from the byte streams, and it took a few days, maybe 2 weeks over Easter this year. And then we had a finished decompressor. So it's a Python script. It's also published on my GitHub, and you can just throw a firmware file at it, and it will extract all the uncompressed binaries partitions out of it. And there is a browser, there is a main operating system, etc., etc. So really, really interesting stuff. We had the decompression figured out completely just from the data. And then Igor pointed out that this is actually a variant of Fujitsu REL, Rapid Embedded Lossless Data Compression. And yeah, it's also used by some other camera models, and it is a hardware block inside of Fujitsu ARM CPUs. So there is no decompressor because it is done in hardware. The bootloader just tells the hardware, hey, please uncompress the following range of data from the flash, I guess, to RAM, and then the hardware does the job and tells the bootloader, here it is, you can jump into it. It's also part of some Fujitsu microcontrollers, and it is actually something that got published by Fujitsu in, I'm not quite sure, 2003 or 2005, and they have even a website related to it. Luckily, we figured it out after understanding the byte stream and fully decoding it. So it was a very, very interesting moment for me. Kind of felt like Homer when he saw this one. Now, we have this PCAP from 2013 where the hotspot check has been captured, and it is querying the GLD Samsung OSP.com site. OSP is probably open source project, and the response is an HTTP OK with body 200 OK. So this is a bit strange, but anyway, this is what I captured, and I replayed it perfectly byte for byte, including the TCP segmentation issue that I mentioned earlier, and the camera just didn't take it. So the firmware released by Samsung in October 2014, and they actually did 2 releases in October 2014, and the first one had a different detection mechanism, and the last one had this check inside. So essentially, it is getting the response from the server, and it is checking for the presence of an E-tag header. It is checking that the server is a variant of Nginx, which was already the case back in 2013. And it is checking for a 0 content length. So the body must be empty. If you don't know this, then you are out. You can't guess this sort of thing. So really not having the firmware binary made it impossible to re-implement that. But once I had it, it was really, really easy. So these 4 lines are generating the correct response that the camera expects. And we did it. Hotspot detection works now on all 27 camera models. And you can just use your camera to upload pictures. For example, using this interesting €10 LTE modem, which was reported by Hackaday back in 2022. It is based on Android 4. But you can enable USB debugging, and you can install Debian over the original operating system running on it. And with Debian, you can install Python to run the API service. You can install Network Manager for the hotspot and DNS mask to do the DNS-based redirection. All you need is to add USB power. Or there's actually an update to this, and this little piece is kind of follow-up. It's also running Android 4.4. I haven't managed to get Debian native on it yet, but it's running Debian in a change root. So I'm going to use this for the live demo. I hope it will work. And it's Android 4.4 with 500 megabyte, I think, Debian installation in a change root for a 500-line shell or Python script. Kind of a bit of an overhead, but, well, it works, hopefully. So how does it work in practice? And now I'm going to switch to the document camera. This is the camera. I'm not going to photograph you, but I have a few pictures. So here's one from another project that I'm a little bit involved in, XMPP. And I also have a Blahai, and we are going to send this Blahai. Oh yeah, of course. Let's take a photo of Blahai. Just a moment. This is not the fastest camera, but it is the only one with Linux that also supports sending to social media. The newer models don't have it. Okay, let's crop the image. And there is a menu. We can share the photo. We can choose Facebook, Picasa. There's email upload. There are also some things like all share and Wi-Fi direct, which only work on the local network, which we are not going to present. Then we have searching for Wi-Fi network. So it is going to connect to this little thing here. And it is not working. Bummer. Let's see, what is the issue here? HTTP 400. So I don't know why it didn't work, but in principle it should have worked, and then it would upload the picture. Maybe we can do another test run. No. Yeah, and the email interface has a very nice feature. It is remembering the last email addresses that you have been using. So you can use this as a shortcut for different upload mechanisms. So you can actually kind of have an address book where you decide if you are going to post it to Mastodon, send it to some of your friends, or whatever. Yeah, it's connected to the Wi-Fi network, and it's connecting to the API, but the API is returning HTTP 400 for some reason.
Because it can't connect to the upstream?
It's using this Wi-Fi. Yeah, the question was whether the camera can access the Wi-Fi network. It's actually user error. So the problem is, I didn't supply a message. And without the message, it will just refuse the upload. So I need to use a different menu in the camera, actually, to upload a picture with text. And then, here we have the shark. Need to put a play button. And I can define the text message. And I need to use a tilde character. It was with J at the end, right? And then we are re-uploading. It takes a moment because after the upload has completed, it needs to connect to the API. And we can switch back to the presentation mode. And here we have. Thank you very much. Yeah, it's supporting most of the camera models. A few of them I just don't have, so I'm not sure if they work or not. And some models are special because of this off-by-4 error and because of undocumented APIs. And also a bunch of the models, the ones with the yellow dot, are refusing my social media login request response. And I don't have firmware for these models to understand what they are asking for. The whole project is located on GitHub. You can find the history of reverse engineering and an overview of the camera models on my blog. And here's also a link to the LTE stick by Hackaday. And yeah, the QR code is to the presentation that you have seen. Thank you very much. Do you have any questions? One moment.
So initially you needed to hack the camera with the etc hosts file, but that's not necessary for the final stage now, right?
You need to redirect the traffic in some way. So the host names that I have shown, they are not provided by Samsung anymore. You either have to put them into the etc hosts file on the camera, or you have to do the DNS redirect using your Wi-Fi network.
Which is much easier than...
It's usually much easier, yes. Especially given that the first model doesn't have a writable root file system, so you have to do bind, mount, trickery to accomplish that.
Okay, thank you.
Thank you. Okay, no more one more question.
Yeah, thank you for your talk. My question would be, are these cameras worth getting? Like, on the used market, are these good in a optical sense, or?
Yes and no. So the compact ones are not really competitive with modern smartphone, except you are looking for long-range zooms. The higher-end models, like this one, are actually quite worth the money. So if you are looking for a camera with an interchangeable lens, then this is actually a good model, and they have rather good used value.
And is there any other work being done on these cameras, like hacking the camera apps or the filtering or anything?
For the second generation of Tizen models, which is the NX500 and NX1, there is a modding project that attempts to add additional features. So there is a user interface. Maybe I can even show it. I just need to switch back. Let's see if this is not very good because... One moment. There's a project to add features to the camera. So it has an additional menu that you can trigger by a hotkey. And then you have things like an additional time-lapse mode. You have a way to disable the 30-minute recording limit for videos, which is mandated by EU taxation laws. And the camera actually comes with a web server where you can remote control it. So you can just put it on your balcony or wherever and remotely access it. I had this prepared actually as, let's say, a fallback for the live demonstration. When the Wi-Fi is enabled, so it needs to connect to the Wi-Fi first. Then I can control the camera from the browser. Can we switch back to the presentation, please? Thank you. So this is a remote control, which is running a standard web server on the camera itself. So now that it is connected to the Wi-Fi, I can switch it to regular recording mode. It's a little bit slow, and I guess I need to turn on live view again. Okay, this is a demonstration effect, I guess. Okay. In theory, you should see the live view from the camera here, but something is wrong. But yeah, there is a modding project. There is not much activity. I took it over after it was dormant for, I think, 7 years or so. But I'm currently doing a little bit more of polishing on it.
So I was wondering, with the encryption and also the TLS or lack of sensible use of HTTPS or anything like that, what would you be generous enough to say that, you know, the chips weren't up to it back then to do all of this on the device? Or?
Well, there is actually a camera that does do encryption, and it's at least one of the camcorder models, maybe the other one as well. I don't know because I don't have it. And it was using not TLS, it was using SSL version 2 back in 2012 or 13 when it was released. So it was not a limitation of the chips, and they are for sure powerful enough to do a proper encryption. It was just not used. And even with the camcorder, it was doing HTTPS with no certificate checks. So it's using the same API, sending username and password, not encrypted with a session key, but instead encrypted with SSL, but without certificate checks.
Slightly related story. I used to work at Twitter, and Samsung had an internet-connected fridge about that era as well. And then eventually Twitter decided to switch off the API that supported this fridge. So yeah, I know it's hard for those companies to keep those things going, but yeah, interesting.
What was the fridge?
It was like a home dashboard thing, and people could, like, I guess...
It was the one that ended up showing an annoying error message at full brightness, right?
Something like that. I just remember them when we switched the API off, and we posted a thing saying, if you own one of these fridges and you can't tweet from it anymore, we're really sorry.
Yeah. Smart devices are fun.
Yeah. And I guess they only support like Wi-Fi 802.11b or whatever. They're not like cameras. I mean, they're not
The high-end model actually comes with 11A, and the other ones I think are 11B or 11D, so 54 megabits or something like that most. Okay, thank you very much.